So, yes, so today we'll talk about Chern classes. So the idea was that, remember the logic, what we want to do enumerative geometry. Enumerative geometry we do using intersection theory. Intersection theory we use using intersecting cycles. And then the first idea that I started with, and then we developed this and checked this, is that we can in fact intersect cycles and the appropriate objects were the Chow group of smooth varieties, and in the Chow group of smooth varieties it makes sense to intersect cycles, and then afterwards we can get some numbers out of this. We'll come back to this question of what to do with these numbers a bit later. So for now we're just working on getting numbers out of geometric things. So now the next point that we are dealing with now that I introduced vector bundles was the following, is that it's great that we have cycles abstractly, but I mean what are the cycles? What are all cycles that we consider? Well, I mean we just take a variety and then we look that has local coordinates, some affine chart. On the affine chart you can maybe I'll write it here because I don't like this blackboard. So I'm just trying to explain the logic of what we're doing now. So the problem is the following. Interesting cycles. So the problem is that in fact we have a method of constructing all cycles formally, which is that we just take our variety X, which is let's say it's projective because that's where we can intersect the best, and then we just take some local chart, some affine chart, and then yeah, it's an affine chart. So affine means it's in some, it can be thought of as being in some n-dimensional or let's call capital N here maybe, capital N-dimensional affine variety. There, this has coordinates, and then you just, what subvarieties here are, we know they are just given by equations given in the coordinates of this AN. So from here we can construct equations, and then they give you subvarieties here, some y naught, some subvarieties in here. The equations give you that. Of course, these are systems of algebraic equations, and then once I have this u, then this y0, then I can say close it, and then I can get some closure. I can close it, and then I get finally some subvarieties in X. Okay, so I'm just explaining for now what we can do with the object that we constructed. These are actually all the subvarieties of X can be constructed this way. So this is the complete description. The problem with this, of course, that as sort of the whole point of also introducing manifolds is that most of the time we cannot construct any reasonable local coordinates on the varieties we construct. They are very, very difficult. They are not normally given in the form that we can do this. So in fact, this gives you theoretically all the subvarieties, but actually if you want a concrete one or interesting ones, they almost never come from equations like this. Okay? So that's sort of the issue with which we are fighting now, and what we are doing, and so I started doing last time, is just to construct now more interesting cycles that appear on, say, projective or arbitrary quasi-projective varieties. And these cycles are the Chern classes. Okay, so interesting cycles. These are the Chern classes of vector bundles of vector bundles. So what we discussed last time, we have sort of the two things we need for this. The two objects were introduced. So one of them is just we've seen so if this vector bundle has just rank 1, so we have a line bundle. Then to this we simply introduced the first term class, so line bundle only has a first term class. And if we had, and so this actually gave us a map from, maybe like this rather, and then this gave us a map from the Picard group of X, isomorphous class of line bundles, into A1 of X. So this was one thing, and the other thing we defined, then we defined vector bundles. And we studied a little bit what it is. So that's going to be VB. We have VB and LB. Okay, so we've seen this. So one beautiful thing, if you take some courses in topology, of course, we do try we stay for simplicity most of the time, even in this discussion, in smooth category. But of course, one of the wonderful powers of algebraic geometry that you can also define a lot of things in the singular cases. So when X is not smooth, and in particular, so that's what last time I explained, that you can define vector bundles. Basically, anytime you have, cover something with affine charts, afterwards on each affine chart, the sheaf is locally free. You glue it together, you get a vector bundle. So you have a meaning of what a vector bundle is in a singular variety. In the topological category, this would be, or smooth manifold category, this would be very, very difficult and technical. And algebraic geometry gives this to you for free. So this is a sort of a key point here. I'm pointing it out because, of course, for simplicity of explanations, most of the time I will talk about smooth varieties for now, at least. That will hide this big advantage that we have here. Okay, so let's just look at what we have. So let's assume that for now, and that will be the beginning of the discussion, let's assume that our variety has many sections. So goal now, so the goal is that to each vector bundle V on some, well, for now, let's just assume it's smooth. But as I said, this is actually not necessary, it turns out. I want to associate, so this is, let's say, I'll put here, this is really bad notation. I shouldn't teach you bad notation, so, okay. So, so let's say rank R vector bundle, so V has rank R. We will associate now a sequence of classes. It will be C1, V, etc., CR of V, where Ci of V is a class in AI of X. Okay, so this is choice. So I'm planning to introduce interesting cycles associated to vector bundles. And the point is that vector bundles, on the other hand, they arise quite often in some very natural way. So, and they're easy to describe quite often, even without finding affine charts for which you would need coordinates, right? So we've seen basic examples of vector bundles you should think about are the tautological bundles on Grassmannians that I introduced before. Okay, so So yes, let's see now. So, let's assume now that we have enough sections. So yes, we'll assume that V has many sections at the beginning. Okay. So let's actually look at a simple example first, just the first one. So we already understand the rank 1 case. Let's look at the rank 2 case. So then the situation is very simple. We can easily describe what, or it's easy to make up, but what possible thing could we ask for, right? So there is basically two things we can do. If I want to describe C1, then we already have a prescription for that. So again, rank V is equal to 2. So then to construct C1 of V, I will just reduce it to the previous case. So what I can do is I can say that this is just C1 of a line bundle. And from a vector bundle of rank 2, it's easy to construct a line bundle. We can just take wedge 2 of V. So this is the second exterior tensor power. I don't need to explain this. Because this is a top one, sometimes I will also denote this by determinant of V as a notation. Okay. And so now this is a line bundle, and we can just consider this as the definition of C1 of V. And so remember what C1 of L was. I mean, C1 of L was, well, if you had a good section, then the definition of C1 of L was just the zero set of a section where gamma is a section of L. So we can very reasonably define a C2 of V is just also as gamma equals 0 for some reasonable section. So now we have this. Okay. So I would like to make two remarks. So this is a definition. So I'll explain the general definition later, but this is the definition for the rank 2 case. Rank 2 case is a little special because we can really do something very natural in this case. So I want to make two small remarks here. So the first one is the following, is that this one, in a sense, we can really define already just knowing what we've done already. So basically, this is already included in an explicit manner in our Chow group story. So why is that? Because you see, the way to think about it is that, in fact, there's another thing here, which is there's another map, which is we can call, well, I can just call it 0. V for now. I'll just have this. Maybe no, this is too much. Sorry. So let's just call. Let's call it gamma 0. So this is a vector bundle. Over each point you have a vector space. So gamma 0 just means that over every point in X you choose the 0 point in V. Okay? And this is clearly an embedding. So gamma 0, but actually any, generically, and in fact any gamma. But gamma 0 is actually an embedding of X into V, clearly. And gamma in general is also, well, it's not necessarily an embedding, but, it is generally an embedding, what I'm saying. So the way you can think of, so actually X can be thought of as a subvariety of V, and the general gamma can be thought of as a deformation of this subvariety. Clearly, gamma of X is equal to just gamma 0 of X in the Chow group of V. Right? So you see, that's because we can just easily deform one into the other. So we can just define a family, for example. You can just look at the family of, well, this is sort of a homotopy. It's not precisely rational equivalence, but you can easily make a rational equivalence out of this. So just informally, lambda gamma goes to gamma 0. Lambda is just a complex number as lambda goes to 0. And so you can easily make a rational equivalence out of this. So you can show that the two are equivalent. Okay, so so it's not a complete precise proof, but you can easily make a precise proof out of it. They are obviously homotopic. Okay. And so what is the interpretation then of C2 of V? So C2 of V is just, can be interpreted if this section is, well, sufficiently transversal, which you can assume, then it is simply X intersecting X inside inside A, and then if you want, I mean, you can pull this back. Sorry. So I pull back by gamma 0. I identify. And this is happening in So what I'm saying is that you can think of the second Chern class is simply as just self-intersecting X inside the vector bundle, and then, well, and just pull it back, that self-intersection to X. And that gives you a class in the Chow group of X. Okay? But now we will have to define the more general, and that will take a little more effort, but it will be similar. Maybe before I go on, though, let's just go back to my favorite example. You know, my favorite example is the Grassmannian, an example, the Grassmannian of two planes in four-dimensional space, which there is some unfortunate thing about notation, which the fact that algebraic geometers think of, projective space and linear subspace of projective spaces, and I like to think about linear spaces. So maybe this. Well, I think this is the notation that they use. So these are just lines in 3 space, projective lines, 3 space, and this is just, it's the same thing as 2-dimensional subspaces in 4 space. So is this clear? So I don't know how to explain this. Okay. Okay, so as we discussed before, we can just define this universal subbundle, which is just the incidence variety. So we just for, well, you can just sorry. So this is just some subspace E in Well, this is the general definition, right? So we have a perfectly well-defined subspace like this. And so as we discussed, we can easily construct sections of this subspace in the following way. So this will be relevant. So what we do is the following. Well, I'll actually do maybe, well, it is A4, but let's just, it's better to know what, sorry, so no. I need another notation, so it will be W. And so, I'm sorry, I'll just, here, and so this gr, now I'll think of as gr to or of W. Okay, so I just take a general space in which I don't choose coordinates, so I just prefer a coordinate for writing, but it's the same as before. So this is useful because now to define, I'll define sections of these bundles. So if I have, you remember this construction, if you have a map from V to, well, C, I just assume it's over a complex number. This is a linear map. Then you can construct a gamma mu, which will be a section, this is a space of sections, of S star, gamma mu of E is just mu restricted to E. Okay, so remember this construction, if you have a global linear function in a space, you can, for each two-dimensional plane, you can just restrict that linear function on that space, and that will give you an element in the dual of that space. And yeah, so this is now. So then if you remember, I'll take, for example, now to perform this calculation, let's do, well, mu1 and mu2, now a map from W to C. Okay, so first let's just calculate just a sec, yeah, C. What is C2 of S dual? Okay. So it will be C2 of S dual. So this is, by this definition, by this definition, C2 is where the section is actually 0, and this the section is given by the 0 set. I will pick one of these. So it's just what we need is that for each two-dimensional subspace, that linear function should be 0 in that subspace. Right? So let's write out what this is. So this is just the set of E's in the Grassmannian such that mu, so mu could be now, I say mu1, doesn't matter which one we take. So mu1, say, restricted on E is equal to 0. So maybe you say it some other way. If I take the space, say, W1 now, well, let's call it K1, just the kernel of E1, so of mu1, this is a three-dimensional subspace, then this simply means that E is in this space K1. So we have a three-dimensional space, and we look at the set of all two-dimensional, all two-dimensional linear subsets W, which are in this three-dimensional one. Okay, so this is the cycle of C2 of S star on the Grassmannian, and this also works for higher rank. And there is a clear, actually this is an identical, clearly generalizes to higher rank. I'll mention that before, I'll mention it later. Now, what about C1 of S star? Okay, so now we just need two, that's why I needed two sections. Now I have to take a section, right, of wedge 2 of V and take its zeros. So let's do that. So this is just, so I'll take this line bundle. I want to know, to construct a section of this line bundle and check when the zeros of this section are. So let's do that. So this will be, so this is, so I'll take the two sections, gamma mu 1 wedge, gamma mu 2 is equal to 0. So this is the set, right? Because I want the this is a line bundle, wedge 2 of V, and to determine its first Chern class, I need to construct a section of this line bundle and check where the divisor of that line bundle is. And how do I do that? Well, what I do is I go to the original V, original W. I take two linear functionals. To each of these linear functionals, I have a corresponding section of this bundle. And then I take the wedge product of these two, and this wedge product now is a section of S star wedge S star, right? Which is wedge 2 of S stars, which is what we want. Okay? And so what I want is this set. So the question is, so what is the, so this is, I think this is one of your exercises, no? Or something like this. Okay, so you know now what mu1 is, mu2 is, there's k1, k2 if you want. So what is this cycle? What is this cycle of where the, so this is the same thing as if you like, so if I want to continue this now. So this is the same thing as gamma mu1 and gamma mu2, so sorry, no. So this is equal to, if I write it differently, is the set of E's in the Grassmannian, so two-dimensional, remember these are two-dimensional planes, such that mu1 restricted on E and is, and mu2 restricted on E. So this is now a two-dimensional subspace with two linear functionals on it. And I want these two linear functionals to be linearly dependent. So it just should be collinear, basically, right? That's what it means, or collinear. So what that means, what does it mean, collinear? It means that, right, so you have it's a two-dimensional space, like the blackboard, and you have two linear functions on it, and you want them to be collinear. So what does collinear mean? It just means that the kernels should be the same, or at least one should be containing the other, right, if they are. So generically, this simply means that so more or less, it just means that the kernel of mu1 is the same as the kernel of mu2. This is not completely true because almost true, right? It could be that the kernel of mu1 could be simply 0, or mu2 could be 0, or okay, so this is the precise thing. So these are the two possibilities. Yeah? So and what does this mean? It just means that so you have these two three-dimensional spaces which are the kernels, and now it's really easy to see that what this really means is that the so this condition is the following thing. So I have this K1 here, so I can take at K1 intersecting K2. So these are the two kernels. And now this is some two-dimensional, let's note it this way, if they're sufficiently generic, then we can assume that in case 2. So now I have another two-dimensional linear subspace of W, and what I want is that the two kernels should intersect, so that will precisely be this common intersection will also belong to this K. So actually, this curl mu1 and curl mu2 is, curl mu1, curl mu2, this is all restricted on E, of course, here, this thing. So since this is the intersection of the two global kernels on W, what you want, both of these things, these one-dimensional spaces, generically, will be a subset of this two-dimensional one. And so that means that, in fact, the intersection, so for this thing, the intersection with E, the rank of this, so this is two-dimensional in W, which is four-dimensional. So generically, this is 0, but what this tells you that this is not 0 is at least 1, because this intersection is actually contains both of these things. Okay? Okay, so this is the meaning of the cycle here. So the two cycles, one of them we get is just when two linear, so what this means is actually precisely the cycle that we're interested in. You remember, this is now one way of thinking about it is this is precisely, if you do it in the projectivized version, so in thinking in G13, even though I don't like this, but now, this means that, so two lines intersect in three space. So is this clear? You don't seem to be very, is this clear what I just read now? No? So let me just explain. This is very simple. So you know what but you understand what this correspondence is between G13 and Gres24? Yeah, so it's just, so for each each two-dimensional space, so the way to think about it, I'm sure you've seen this, right? So you just take the four-dimensional space, and this is W, and then you take a three-dimensional space which does not go through the origin, and then for every two-dimensional subspace, you look at the intersection that gives you, so this is three-dimensional subspace, you get a line, right? So in 4 dimensions, you take a three-dimensional space, somewhere you fix it, that will be your affine space, and then you get a correspondence for each two-dimensional, so this is E, and this is say W0. I should write it here. Let me explain, just to be sure this is clear, right? So I have W0, W3 is a nonlinear space here of so this is some affine linear subspace, and then if you have that, then for each E, for example, which is two-dimensional, you can associate E intersection W0, which is now, this was rank 2. This is now just a line, it's rank 1, because you lost one dimension here. So when you assume that the rank of two planes, K and E, the intersection is at least 1, that precisely means that the two lines intersect, right? Because for them to be rank at least 1, I'll now take another plane and another line. Of course, now you don't see it, right, because it should be three-dimensional, this W, and then they don't intersect normally. But saying that there is an intersection means that there is a common part here. Like that, and then there's this intersection point. So this is what the meaning of this is, right? So the meaning is that E intersection W0 intersecting with K intersection W0 is not empty. Okay. So this is precisely the condition that I was trying to see at the beginning of having three-dimensional space and lines the condition of lines intersecting. So that's precisely the first-term class of this tautological bundle, the Grassmann. Okay, so let me now also finish with the general definition. So general case. So these were the 2 points I wanted to make. So now you have V X, and you have gamma I. So this is rank R. And you have gamma I, you have a bunch of sections. Okay. And you define, so Ci of V is just defined in the following way. It's similar to this. You just say that, gamma 0, gamma 1, etc. Gamma, so here rank R, here you have dimension now n, gamma n minus R is 0. Okay, so this is a definition. So this is if you like, you can think of this as being a section of a bundle which is wedge n minus R plus, n minus R plus I. All right, so let's just check that I did this correctly. So if, no, this is stupid. No, I'm just doing something stupid, sorry. I'm just, sorry. Now I confuse myself, just a second, with some other formula. It's, it's just R minus I. Let's try this one. Let's see if this works. V. So C, this looks more promising, right? So if V is rank 2, for example, then C2 is equal to, so now it goes from 0 to 2 minus 2, right? So this is just 1, the gamma 0. And then C1 is just equal to, so then I is 1, so then you have, that. So we'll discuss it. Yeah, sorry. Okay, so I'll stop here for 15 minutes, come back. Yes, so now I gave a definition for the general set of Chern classes, and this is just this. So maybe I'll just give you now the main theorem. And this is the following. So as I said, I'll just formulate for smooth varieties, but it works for in any case. And this is the following. So X, so I'll just put it smooth. It's not very important. V rank R vector bundle. Then there are Chern classes that exist. There are CI. So there's a way to associate CIV in AIX for I going from 1 to R with the following property. So there's the following properties. So there's a way to associate to each vector bundle a set of, as I said, and this is an example of that, cycles in the Chow group with the corresponding codimension where I goes from 1 to R. And so these are the properties. So just before I forgot one. Ah, yes. So I introduced a notation. The total Chern class, so this is just one, so I can just put them into a series if you want a formal series V, and I associate to 1 plus C1V plus etc. plus CR plus CRV. Okay, so I just put them into a generating series. So this is now an inhomogeneous element of the Chow group of V. Of course, this has degree 0, 1, well, upper degree, so, and this has degree R. So this is a strange thing to do, actually, because now they do not preserve the codimension, right? Okay, but anyway, we have this notation. So the first, so I'll now, there exists such a thing, and I'm listing the properties now. And it will use this notation. Ah, sorry, I sorry. I just was too stingy because you can't see anything down here. So I didn't want to use another line, but I should. So V, this is the total Chern class, C of V, so without the index. And this is 1 plus C1V plus CRV. Okay, so this is the notation. And so here are the properties. So the first one, that this is just an extension of what we already defined using divisors. So for R equals 1, it's the obvious thing. C of L is just what we defined. So it's a little bit tautological, I'm sorry. But by this, of course, this is, as I said, it's tautological, but the idea is that it's an extension as defined earlier. Okay, so it's an extension of that. So the key two properties are the following. One is that's called Whitney's formula. And this says that if you have an extension of vector bundles, of which we have many examples, so you have, for example, a subbundle, a vector bundle, and a quotient bundle. And this is, I don't put the zeros here, but this is an exact sequence. Or maybe I should, and it's easier. So this is an exact sequence of of vector bundles then CV factors as CS times CQ. Okay, so this is the key story. So as you can see, I mean, if you think of this map of mapping vector bundles into the Chow group, then you get a great simplification, because basically you split, if you like, every exact sequence. So whenever you have an exact sequence, it just becomes a product. So if you like, every exact sequence is like a direct sum. There's no difference if this is V is a direct sum of S of Q, or if this exact sequence is a non-trivial extension that does not split. The answer is the same. So in a sense, it's really something very, very simple, you could say, in terms of structures of vector bundles. Okay? So the other thing is what's called naturality. And this just says that if you have, again, I'll just assume that, so this is morphism of smooth varieties. Smooth varieties. Then if I look, then as we discussed, you can pull back vector bundles from V. So let's take a vector bundle V and X. You can pull it back and have a vector bundle, which is the pullback of the vector bundle. And that just essentially means that you just pull it back, each fiber over the, to find the fiber. Here you just look at where that point goes and you pull back that vector space, which is the fiber over X here. Okay. And the point is that, so now we have a sort of an exact triangle. We can do two different things. We can pull things back in terms of pulling back just a vector bundle in a simple, kind of naive way. And we can also pull back cycles, which was a more complicated operation, pull back cycles in the Chow group. And so the claim that these two things are the same. Okay, so this is the second property. Okay. So we not only, so the amazing fact, and this is what we'll explore next, is that we not only got just a sequence of natural cycles that we get from vector bundles, as we got a very powerful calculus of manipulating these cycles. And this is what we'll take advantage of, and I'll try to convince you of this now. Okay? But before that, I have to, so I will not do much of the technical stuff. I mean, in general, my philosophy is that I'm not giving you all the technical proofs of the statements. Rather, I give you little exercises that look like, the beginnings of the technical statements, like this thing about flatness and things like that. But then we don't carry this through to complete proofs of things, because that would take a much more longer basic course in algebraic geometry. So what I wanted to say, I want to make 2 points now. So the first one, okay, so this is a statement. Maybe, I'll just first, maybe just example 0, to understand how this is consistent with what we've been doing, is that, let's just take the simplest case of, and this will actually be a crucial point, is let's just look at X, and let's assume we have two line bundles on it. So I'm not right L when I write L, then it's always a line bundle. So then, of course, you can easily construct a vector bundle on X, which is just the direct sum of the two line bundles. So this is now some vector bundle of rank 2. So I just want to just have a first sort of exploration of this equality. So then, according to Whitney, says that C of V is equal to C of L1. So then, of course, it's a direct sum. There's always an exact sequence, right, in a direct sum. So I can write that this is just this, and this is just 1 plus C1 of L1 times 1 plus C1 of L2. And this is just 1 plus, and now I take them degree by degree. I get C1 of L1 plus C1 of L2. So this is the degree 1 part, and then plus C1 of L1 times C1 of L2. And this is the degree 2 part. Right? When I just open the parentheses, one of which is missing. Okay? So let's see what we got here. So so this is kind of obvious. So let's assume that I have sections. I choose this. Of course, now, if I want to choose, I just want to compare this now to what we had before. Okay? So let's just choose sections that is gamma 1. So gamma I will be just section, well, let's just say gamma 1 is section of L1, and gamma 2 is a section of L2. So the point is that then gamma 1 plus gamma 2 is going to be a section of V, right? And so then we can now study, compare what we've done before, and obviously, of course, it will work. So what does it mean? So let's try to understand what is the say C2, for example. Let's look at C2 first, say, okay? So C2 of V, according to that definition, it just means that gamma 1 plus gamma 2 is 0. And this is, of course, can only happen in a direct sum if both of them are 0. So this is just the intersection of gamma 1 equals 0 times intersection gamma 2 equals 0. And this, of course, this is now L1 and CL1 by definition, and this is C1L2 by definition. And the intersection is precisely the product in the child group. So you see here where I should get C of V, here I should get C2 of V. And this formula, this Whitney formula, says that C2 of D is the product of these two, and I verify it, and it's actually consistent. If you, okay, indeed, I constructed a section, and the corresponding 0 set of the section is actually the product of the two line bundle things. Okay, so let's do the other one. So there, I need a slightly different thing. I need to have, so now I do C1 of V. And C1 of V should be that a gamma 1 wedge gamma 2 should be 0. Right? So what does it mean gamma 1 wedge gamma 2 is 0? In a direct sum. So how could two of these sections be collinear in a direct sum? Only when either of them is 0. If none of them is 0, they cannot be collinear because it's a direct sum. They point up in different directions. So this can only happen if either gamma 1 is 0 or if gamma 2 is 0. Okay? And of course, it's the corresponding class. As you can see, it's precisely the union. So it's in the Chow group, the corresponding class is C1, and it's a sum of Chow classes, which corresponds to the union. So this one corresponds to things. So here you see the consistency of that definition with Whitney's formula. So this theorem is sufficient to calculate it in most general case, but so part of the theorem, actually, these properties also define the Chern classes. Note that I only define the Chern classes when you have many sections so far, right? So actually, there's no definition yet, only a theorem about how it exists. Okay. Now about this theorem, so well, maybe I do this one. I'll just do first the general construction. For now, this will not be so important for us, but just for I will come back to it maybe. So by this I mean, imagine that you don't have a sufficient sections to construct these intersections. I mean, there are vector bundles which don't have any sections, right? So remember, so the problem is just, it's sort of a technical one. You remember, for the line bundles, we know how to solve this problem because we could do rational sections, remember. So recall that this we could do, C1L is a line bundle. Then we knew how to define a C1 of L is just the divisor of gamma, where gamma is a rational section. That was the idea. And rational sections we know how to define because since line bundles are locally just constants, you just, these are, it's meaningful locally describe so locally they're one-dimensional, so sections of line bundles are locally just functions, and rational functions we know how to define in algebraic geometry, so this is kind of a basic thing. This is easy. But for higher rank bundles, this is not so clear. So remember, so we do have a definition of Ci for C2, for example, for high rank bundles, but if there is a section. But if there's no section, I would have to say what a rational section of a rank 2 bundle is. And this is not so clear what that would mean. Because we cannot divide anymore some IC2. In order to say something is rational, you have to be able to divide. And if you have a vector function, right, so locally a section, a C2, as locally is a vector valued function. It has 2 values. And it's not so clear how to divide by, so how precisely. So this is not so, so this is not a path that one takes in this situation. So we need some different trick. And so the different trick, so I'll just explain this now, as I said, it's just a definition. It's the following. So the construction is the following. So suppose we are here. So the first step is that we can actually construct another variety, which you could call Y, which is just the projectivization of V. Okay? So now this is a compact, it's a proper map. And so this is clear what it is. I mean, a point here is just, so let's call this, say, pi. So pi inverse P is just a projective space, Q, so for Q in X. If I take the fiber here, this will be simply the projectivization of that vector space that we have. It's just equal to the projectivization of V let's call this pi 0, of pi 0 inverse Q. Right. So to each vector space here, you just associate a projective space there. Projectivize, and it's easy to, one needs to show something, but it's very easy to show that this is a nice variety. Okay? Is this clear? So you have for each point X, you have, say, a 2-dimensional space. If the rank is 2, then you will get a P1 bundle here, which is just the lines. So this is just, so if you like, these are just the lines. So this also you could call VQ if you like, as a notation. And these are just the lines in VQ. Okay. So maybe let me just give an example, because this is, anyway, it's useful. So for example, let's just take the simplest. So let's look at this 2-4 situation. you look at the tautological bundle. So this is our setup. So how can you formulate what the points of this thing are? What is PS? How can you define what is PS? So that means, so S is just a point in the Grassmannian is just a choice of a two-dimensional subspace here. And now what is PS? So in PS, in addition, I choose a line in this two-dimensional subspace. So actually what this space will be then, this is the set of, they're called flags, partial flags. So I have this L, S, and then I have A4 here, right? So this is one-dimensional, and this is, well, the notation is a bit poor, but anyway. This is 2, so this is rank 1, rank 2, and then 4. So this total set of possibilities of you fix a four-dimensional linear space, and you look at the total set of possibilities of choosing a two-dimensional subspace, and then in the two-dimensional subspace you choose a one-dimensional line. And you take the set of all these, it turns out to be a compact, beautiful compact variety, and that's what this PS is here, for example. And you can, of course, do this in general. Okay? Now, what is important here, so this goes under projectivization. Projectivization of a vector bundle. So it's great. Of course, this one will now come with a line bundle O minus V, whose push forward is precisely V. So it's easy to see. So these are all very easy exercises, but since it's not central, I'm not going to do this here. But it's easy to see that this comes. We also have, so it's a generalization of O of 1. This O of 1, or of V, if you like, which is over this PV. This is the sheaf, and if you want the line bundle, actually it's the usual total, so I can easily explain what this is. This is just the dual tautological line bundle to this one. So actually the corresponding line bundle, there is some line bundle L, and the corresponding line bundle is is precisely, well, it's L, but actually the tautological one is L minus 1, the dual of it, and a point in L. Now what is that? So now it's no, this is now bad notation, sorry. I need some other thing. Yeah, I'm sorry, I just have to change this because otherwise, so sorry, could you please change this? So let's call this E. It's some two-dimensional space, and for this line, I'll just use some F for now. And this is a set. So what I mean is that this PS is just the set of these things. Okay? Now I go back to the general case. So then, well, I'll just denote them this way. So I have this O of 1. Now to understand what it means in terms of line bundles, let's just take O of 1 of minus 1. Now this is a locally free sheaf to which vector bundle corresponds, a line bundle. Let's call that F now. And so F is a line bundle here. Okay, and so what is the fiber? So what is the fiber? So I have X, I have V, right? And I have the projectivization of V. The projectivization is the set of lines over each fiber, and F is the tautological line bundle. over PV. Okay, since you remember, the PV is a set of lines, and I just take for each point, I take the corresponding line, just like the tautological line bundle was there before. Okay. So this is our construction, and this is actually, I mean, calculation-wise not completely trivial, but we'll see how this works. So the theorem says the following. And I think in topology it's called the Luray-Hirsch theorem, it's called something else. But the key point is the following. It's now a generalization of what the Chow group of the projective space should be. We're going to describe the Chow group of this thing. So actually, so first approximation is that the Chow group, so we have a map now from PV pi to X. So we also have a map of Chow groups then, of pullbacks. And so the pi upper star mapping the Chow group of X to the Chow group of the Chow group of P of V is injective. And so that's one thing, but what is great is that we actually have a great element here, and this is something that does not come out of this map. Okay, so these are all the pullbacks. So the image of this pi upper is just all the pullbacks of cycles from the bottom from X upstairs. But in fact, you have we have an extra class, which is this psi. So we can just take C1 of this F dual. I'll apologize, I'll write, well, F dual. Okay, I mean, but it is just the O, which is the furniture class, the hyperplane section, but in this family sense of these. So this is this F here, the tautological, the C1 of the. So let's denote it by psi. So this is basically, so this is well, this is actually a zeta. Let's denote it by zeta. By when I say not, it means notation, actually. It doesn't mean it's not. That. Okay, if it's not, then I'll cross it. Okay, so we have two things now. So it's not, this is the first part of the theorem, sorry. Number one, and then there is number two. So the number two is that now I take this zeta, and now there's a relation between these. And the relation is the following. In fact, I can even write down more precisely. That actually the Chow group, just like the Chow group projective space was very simple. It was just a polynomial ring. You remember that zeta to the n plus 1 was 0. Well, now that's not true. There's a twist. So, but it's still true that if you take the, so I'm going to actually tell you what this is now. So this is pretty fun. This is just the Chow group of X which is in there. So that's already in there. And now I allow this extra element, zeta. So if you like, these are polynomials in the sorry, so it's the other way around. The Chow group of X is like this, and here I have zeta like a polynomial ring, and then there's a relation. And since it's projective space, I'm just going to divide the relation by zeta to the n plus 1. And if it was just projective, if X is a point, then this would be the end of it. Zeta to the n plus 1 would be 0. But now that's not true. There's a polynomial, this one, correspondingly. So actually it has other coefficients. Okay, and this is precisely Ci, I suppose, is correct. Zeta to the n plus 1. I think it's correct this way. So it's and now my brain is shot, so I don't remember now. Is it I or n minus I? It should be, yeah, it should be, well, if codimension is the same, so it is still codimension I. Is a bit suspicious. I think it probably should be n minus I, no? That seems logical. Zero plus 1 is what it should be. So this is the relation. This should be 0. Okay. Okay. So
here n is the rank of the number, right?
Yes, sorry. So this is not such a good idea. Thank you. R. Okay. So do I have this written down somewhere? I think so. Anyway, I hope I did it correctly. Yeah. So the idea is that this is a sort of a ring. So this is the intersection ring, like the upper Chad groups on smooth varieties. This is a ring defined. Oh, well, this ring, because this is actually a ring homomorphic since it's a pullback. And one ring of the other ring is just a polynomial ring given by a single relation, and the relations are precisely basically the pullbacks of these CIs. And so since this is injective, these basically determine these classes, and these are the kind. So this is sort of the definition theorem. I call this definition theorem because you remember, so the previous theorem already said that these CIs exist, and now I'm giving you a theorem that these CIs are constructed, they're come out of this construction. Okay, so this is just to give you an idea what the general construction would be. And so now maybe just to finish, I would like to give you sort of another point of view on the previous story a little bit. Okay, so yeah, so now I have to get these numbers right. I hope so. So the question is the following. What would be another interpretation of what we have done before of the degeneracy? So sort of the Grassmannian interpretation of degeneracy. Of sections. Okay, so let's look at that. So what I mean is the following. So I just said, let's look, this was also, I make something a little more precise now than before, okay? So the idea is, so recall what the idea was, that if there are sections, I can assume there's a bunch of sections in gamma V, so as before, V is a bundle, but assume now that there are sections, and assume that there are many sections, so there is sort of, well, I'll define, so assume gamma n, so gamma, now let's call it m maybe, okay, so dimension of X was n, I think. I'll just take m sections, and assume that these generate the fibers of V, of this. So is this clear what I mean? So by this I simply mean that for each Q, right, so this means just that for each Q in X, I can take gamma 0 Q, gamma MQ, and then these are just some vectors now in VQ, that fiber, and if I take the linear span of these things, this is really VQ. Okay, so that's what it means that they generate. So let's assume that. So I'm already a little suspicious that I shouldn't have had the 0 there. So anyway. Okay, so what the point is the following, that if this is true, then I think it should be 1, sorry. Then this is rank R, so this I don't change. So this is rank R here, and this is dimension n here, right? So those are those numbers I don't change. And now I take m sections, and I assume that this condition holds, that they generate the fibers. Well, then I have a map from X, so this induces the map X going to the Grassmannian of m minus r planes in the space of, so let's call these so let's look at the linear span of these things. Let's call this, denote this by W. This is a notation, and this is a subset of the space of sections. So I just look at some linear subspace W of the space of sections, and I look at the, well, it has a basis like this. Okay. So then I have a map like this, so this is the point. Right? So how does this work? So the point is that for each Q, I can associate the kernel of the following map, of the map that I have from the space of sections W. For each section, precisely this thing that I'm writing here, so the evaluation of the section above the point Q, those are some elements of this vector VQ. See? So just again, so I have these sections, gamma 1 up to gamma m, and now for every, so I have this map that for each Q in X, I do the following operation. I look at gamma 1 Q, etc., gamma m Q, and these are elements of the just a second, what did I want to say? Yeah, just a second. Q. Just a second, I already confused myself. Oh, this is where. That's not what I wanted.
I think it's fine, right? You have a map from X to this.
Yes, it's fine, but it's it doesn't do what I want. Just a second. So yes, because I missed the duality thing here. This is all correct. Yeah, it's yeah, because I just sorry, it's not perfect. So sorry. So this is a little imperfect. So yeah. Okay. Well, let me just give you the correct definition. I'll just stop here. I don't have to. Okay, so yes, because I choose this basis, but unfortunately, then I want a linear map. And this basis, of course, now, it doesn't give you a linear map. What I want is, if you like, this, well, what I really want is W dual now. Okay, in the notation that I have here, I want W dual. Okay, so let me erase this anyway. It's clear, so I just want W dual, because what do I want? I mean, I want to define a linear map. And so yeah. I'm out of time. Let me just. So W dual is just, of course, it's just basically just Cn, if you like. And so that just means some coefficients alpha 1 up to alpha m. Okay. And now to am I doing this right? And I just confuse myself. And
so consider the sub-bundle of this trivial bundle generated by these sections.
yes, and so now I have a map. Yeah. So that's what I should have done. Yes, thank you. Yes. Yes, so sorry. I just confused myself. That's right. So this was fine. Yeah, so no, this was okay, actually. So I have just that W that I wrote there. So I have a map from W this way into VQ. That's right. Sorry. Yeah. So I just, so these elements form a basis of W. And now this basis of W taken to M vectors in VQ, and of course then they linearly extend to the all of W. So sorry. Yeah. I confused myself one place, but and so what we do is that we associate to each Q the kernel of this, which is, since this map is surjective, I assume this surjective, this kernel is now an M minus R dimensional space, right? So this kernel, the rank is M minus R dimensional, and this way for each X now for each point X now I have a point in the Grassmannian of M minus R dimensional spaces in W. Okay, so this is what I want to construct, but I confused myself in one of the places. Okay, so sorry, I didn't. The point is now, let me just say just one word, and I don't have time to explain it. But so the idea is that now, looking at it this way, we can represent the ith Chern class of the vector bundle as the pullback. Now I'll call this pigre, the pullback from Grassmannian of some special classes sigma I. And so these classes sigma I is that what I'll construct next time. Those are the Schubert cycles that you might have seen, but anyway. So I'll explain this next time. Okay. So this is an interpretation of the construction of the degeneracy of this. Remember, the construction of the Chern classes was that some wedge product of these sections should be 0. You can think of that as simply pullback of certain Chow classes from the Grassmannian along this map. So sorry.